Okay, this is a continuation of the lecture we started on section 1.3, the lecture I gave on January 24th. We got about halfway through, or partway through it, and then I had to stop. Today, which is the 29th, we're having a cold day, not a snow day, so I'm recording this one. I'll pick up where I left off on this one. I'll have a separate recording for the next section that we'll do later today. So, if you remember from the last talk, what we started was with the fit experiment. We got to the end of the block simulation before we stopped, and your first homework, which we handed out last week, was on the block simulation. So today I want to go back and revisit a couple things there real quick and talk about T2 phasing and then spin and go experiments. So let's just jump in there, just looking through the different slides. This is the simple fit experiment I talked about last time, and this is an example where we simply have a simple transmit-receive coil and a sample in the middle of an RF MR scanner. And this is the sequence up here. I won't go through all those details or go through this drawing again, but I do want to talk about this slide. So this was the fourth slide before, and there was some confusion and questions about this diagram I had here. And I made some changes and updated the slide online, so it's version 4, V4. You can go look at that again. Before I come back to this, though, let me explain a little. Go back one slide here to this new slide that I have on here, and talk a little bit about the transmit and receive fields. So to get a little better and a clearer understanding of how we calculate what that signal and in the coil that is generated from magnetization, let's first look at a different case, which is a transmit case here on the left side here. So if in a very similar geometry, if I imagine I have a simple loop coil out here that's perpendicular to the x-axis, and I want to look at if I run a unit current I through this coil, it's going to produce a B field at the position of the origin of this in this coordinate system. So we're going to just make this definition that a unit current I in this coil that produces this B field here, B, at the origin, is going to have this relationship. It's just going to be a linear function of this term, which I'll call, this is a squirrely B, beta transmit. Now, in the previous notes, by the way, I just had a regular B here. That's, I'm really following the treatments from this book, which the green book, which everybody calls Heike, but it's currently brown in the second edition. So if you want some more details, you can come borrow this book or look at your own copy of that. They used a script B, and honestly, the last version of my notes, I just didn't have a script available in my math equation editor. So now this is a script, I updated it, so we'll try it this way. So this is a script B, this beta transmit. And the way you should think about this is really just a sense of proportionality between the unit current I and that field that it produces at this distance away. So this beta transmit is just a scaling factor. And if you look at its units, it's not Tesla. It's Tesla per amp, which makes sense if you look at this equation here. So this transmit field, this beta transmit scaling factor, it describes, encapsulates all the things about how it takes the strength and phase of the B field relative to this current here. So it includes things like the coil area. It includes things like the distance. So obviously, if you're further away, then that beta transmit is smaller. And it is a complex value, so it also incorporates real and imaginary components. It might this beam might not be exactly the direction you'd expect it to be. And it incorporates the rotation of this relative, like if this is not perpendicular to the x-axis, then the field will be a little less at the origin. So all those things, all those complicated things are all wrapped up in this thing, B transmit. And it has these units. Now, I'm going to keep it in the script here because this is how they did it in the text as well. But in practice, this B transmit field is what we call the transmit field. And we're more typically notating it as a B1 plus field, which has a variation in space and is a vector. When we get to the mapping, when Greg Metzger is going to talk about mapping in the future part of the course, or when we're talking about coils in the hardware part of the course, this is the transmit field, even though it doesn't have units of Teslas, Tesla per amp, but it's sort of a relative or normalized transmit field. That's what we typically call it. So keep in mind those two are the same. So on the transmit side, we put a current in there, you get a field over here. The reverse is also true. So in this example, we have a unit piece of magnetization at the origin with a magnetic moment M, and it produces, you can see as this would rotate around, it will produce a B field here in the center of the coil. it's a vector, so it can be in a various direction. And that B field is proportional to the M field by this factor B receive. So this is the diagram here, and this is what people didn't like, that I didn't have my A coil in here. So B receive is the field that's produced at the center of that coil is proportional to the magnitude of that vector with this scaling B receive, and we're dividing out the area of the coil. It just so happens to work that out that the area of the coil needs to get pulled out of here. So this is the same kind of concept. It's just the scaling from that magnetization to that B field, just like this was a scaling from the current in the loop to the B field there. So if you take this expression for B coil and throw it into our flux equation, so if you integrate over the coil the perpendicular component of B with the normal of the coil, and if it's constant throughout there, this is where your A coil is going to come in and cancel out with this, and get your phi is equal to M, the magnetization as a function of time, times this B receive, a complex vector. And this equation right here, I'm going to go forward one slide here, was what I had here. I made this giant jump here, which was unsatisfactory and super unclear. But that's what the issue there was. So again, like on the transmit field, this B receive is not purely a Tesla. It's a Tesla per amp. It's kind of a unit, a normalized transmit field. And if you look at the units, this works out. M is amp meter squared. And so it all works out to be the right numbers. And typically, although I'm using the script B, we're going forward, see this as a B1 receive field. So this is the receive field, and over here is the transmit field. These are the things that we need to map out as a function of space. Another thing you'll notice, I mean, obviously I'm trying to draw a parallel between transmit and receive, and there is a parallel that here's it is, the principle of reciprocity. The magnitude, note the magnitude here, of the transmit field is equal to the magnitude of the receive field. The phase gets a little complicated, especially when you get to higher fields, but the magnitude is going to remain the same on both. And we'll talk about that more certainly in the high field hardware section later in the course. So that's what I was going here with this, and going to the derivation of the signal equation. If you look at this updated B receive here, and now this notation just means it's a complex vector for B1, then these equations should make a little more sense. So that was all just going backward a little bit. At the end of the last lecture, we looked at the signal in the Fourier domain. So we took our free induction decay here and did a Fourier transform as described here. And we got a Lorentzian line. We didn't derive that, although that's a fun little project to do. And we noted that the full width half max of that line, and full width half max, by the way, means if this is the full height here, half the height is the half height, and it's the width right there, full width half max. For our homework, I think you have to do this on your homework. You have to measure that graphically, or you can write a little program to do that. I think that's up there as well. So there's a relationship. If this decays faster, then you get a broader line. If this decays slower, you get a narrower line down in the frequency domain. This might be familiar from a lot of Fourier characteristics, something that's long in the time domain is short in the frequency domain, etc. So that should add some intuition for you. I also, as you when we hand out the homework, I also provided some code online to do some simulations of the FIT experiment. So here's on resonance, the signal, and the Fourier transform of this. And it's not part of the homework this time, but it's worthwhile to go through and look at different offset, different omega values. That what happens in the frequency domain as I change this off resonance term, you can see that the peak here shifts. So here it's at 0 hertz, here it's at, well, it's minus 50 hertz, there could be a sign error there. Here's at 100 hertz off resonance. And what happens in the time, and it looks the same, the shape of the curves stay the same, they just shift horizontally in the frequency domain. In the time domain, it changes the frequency of the complex sinusoid that's modulated by this exponential decay on top. The exponential decay on top doesn't change, it's just the frequency of the sinusoid. I think that's all I want to say about that one. Okay. Next slide. So part of the simulations, and I didn't explain this in very detail, I don't think about how we do it, but there's a few different ways of simulating the block equations, and you'll note that from the previous stack of slides, what we really calculated was the term dm dt. And the one way we can use that to solve, to simulate what happens in an NMR experiment is to use a forward difference approximation. So here, if you have any function, this curve here is a function of time, if you know what the value is at f at time point j here, to calculate it at j plus 1, you take f the value at j, add the derivative of f with respect to t times that time step, and calculate your new value at this time point. So this works, the smaller the delta t, this works quite well. It's kind of a linear approximation, and it's the forward difference approximation. There's other ways of doing this. But as long as your delta t's are small, this is going to be reasonably accurate. And this, in the whole example code I gave you, is exactly how I calculate how magnetization evolves during the free induction decay. And in all the code that I give you is going to be doing that. So to calculate the magnetization, this is just the x component, but this is true for all the components of magnetization. To calculate it at a new time point, take the previous time point plus a delta t times the dm dt, which is the block equations. So you calculate this at time point j, and then add it to and add it to get to the new magnetization state. There's another way to do this with rotation matrices. I'm not going to go into that here, but it's a relatively easy way to do it. But it has the same sort of idea that we have a small delta t, and you can sort of treat it as a linear process during these small delta t steps. So moving into the next topic, which is T2 star dephasing and spin echoes. We'll start with the FID experiment here again. In this example, what I'm doing is I'm doing a simulation of 4 different isochromats. So the stuff I showed you before, we assumed a single isochromat, meaning one little packet of material that has the same frequency, same isochromat, same frequency. And this, in reality, you never can. If you put a sample in the scanner, it's throughout the sample you get a distribution of frequencies. And so this is a very simplified way of starting to look at it. So we're now going to look at, instead of a broad distribution of frequencies, we're going to look at 4 discrete frequencies. And in this case, I took a relatively small spread, so they're 1 hertz spread apart. And this is a bigger spread, so you got 10 hertz spread apart. And in these plots, you can see here, these blue traces are the time domains for the time domain signals of the free induction decay for each of the 4 isochromats with different spread. If I take the complex sum of them, you get something different. Now you can see, like for example, you see this one's pretty far off resonance, so you can start to see a little bit of sinusoidal or a complex sinusoid under the curve. And this one is pretty close to on-resonance, so it looks pretty much like a straight decay. But that's what you're getting, is these things spread out. If you take the complex sum of them, the result is this line, the black line here. The net effect of that is that what it looks like is it looks kind of like what we had when we had very tight a distribution or a single isochromat, except for it decays a little quicker. And this decay is what we call T2 star. It's actually the apparent decay, which is a combination of the T2 that we have up here plus this effect by adding isochromats that have slightly different frequencies. And I'll talk about that a little more. In the frequency domain, here I want to look at these 2 cases here. So here we've got a very tight spread between these, and the black line is the combination of all of them. Remember, the Fourier transform is linear, so we can add them together in the time domain or the frequency domain, or add them together in the time domain and then do a Fourier transform, or the Fourier transform and then add them together. It doesn't make a difference the order you do them. So here you don't see much of an effect when we have a little bit of spread of off resonance, but here you do. So I've got these 4 peaks, and if we looked at each isochromat, you can see they're at different frequencies. This one's further off than the others. When I do the complex addition of these guys together, you see 2 effects. One, the amplitude of the combined peak is reduced, and the breadth, the full width half max of this new peak is also broader than any one of the original isochromats. So this is a visual way of looking at these things, looking at the effect of multiple isochromats. This effect, I mean, normally in the real world you never have 4 isochromats, you're going to have a million, it's a very large number. So you don't see this little shoulder. This is not a nice symmetric line with the black one here, but if you had a lot of them, you would. And I would encourage you, if you want to understand this a little bit, to go ahead and you can simulate it based on the code I gave you in class and look at this yourself if you want to see this effect. So this concept is called, this effect from inhomogeneous samples is called inhomogeneous broadening, because it comes from the broadening of the line width due to an inhomogeneous B0 field. And that's how we're interpreting these 4 isochromats. There are 4, instead of putting a sample in perfectly at 3 Tesla, there are 4 samples that are slightly different, slightly higher or lower than that nominal field B0. And in this case here, if you had a lot of these, I mean, right now, if you looked at that black line, I don't think you'd find that to be a perfect exponential. But if you had a large number of these things, and the distribution of the off resonance was Lorentzian specifically, this would be an exponential decay, and then you could calculate the line width in a closed form like this. This is really only an approximation for the one specific case. It depends on the distribution of those off resonance terms, but it's a good guideline that the full width half max is inversely proportional to the T2 star. So let's look at that in a little more detail. So we talked about T2 and now T2 star, and let's describe it in these terms. There's T2 prime. It doesn't quite look like a prime, but that's, or a T2 dagger, you'll see in some pieces of notation. And what T2 star is the inherent T2 in the sample, so this is what you'd get for a single isochromat, plus the T2 prime, which is the effect due to inhomogeneity. And these two add together linearly. Well, their rates do, so the inverses of these things add together linearly like this. So the rate of T2, which is 1 over T2, plus this R2 prime is equal to R2 star. And R2 star is what you observe in an experiment. That's what you observe here on this previous slide. This decay here is T2 star, or its rate R2 star. You don't ever directly measure R2 prime or T2 prime, but you can calculate it from the combination of these two things. A good way to visualize this is, I'm going to give you an example of one way I like to visualize it. So imagine this is a 3 isochromat case to help visualize what's going on. We have sample A, B, and C, and let's say they're close enough together in space that everything's essentially the same, but they have slightly different frequencies. In this example, B has a negative frequency and C has a little bit of a positive frequency. So if I excite them, and now they're immediately after excitation, they'd all be aligned in this example in the X plane. If I let them evolve over time, this one's on resonance, and so it doesn't have any offset, so it stays exactly still in the rotating frame. This one's at a little lower frequency, so it drifts, and this one's at a little higher frequency, so it drifts over there. So if you look at those vectors and how they might add up, B and C are coming a little off resonant, the phases are accumulating. And if you were to take the vector sum of all those 3, as I'm showing over here, you would notice that the total vector sum of these is less than as if they were all phased together. And that's really what this phenomenon is. It's incoherent summation of these things. And we call this phase dispersion. As the phases of these 3 isochromats spread out, they're no longer uniform, their net combination becomes less. Here, as you can see here. When they come back together, if they're ever back together like this, you would call this phase coherence because they all have the same phase, and this is signal loss due to phase incoherence. So this process here is the T2 prime process that leads to an effective T2 star decay. And one way you can refocus that is the second experiment that I wanted to talk about, which is the spin echo experiment. This is a very practical technique. It's used in imaging and spectroscopy, and it takes a little bit to visualize, so I have a few slides here to wrap up this set of talks. And again, this little diagram I have up here is building on the example I had in the previous slide. So this experiment, I have no gradients on or anything. It's a pretty simple experiment. Like the FID, we have a 90-degree pulse. Here I have it, and then I just picked it, so a minus 90y, so it's kind of arbitrary. It just puts it down. So I'm looking at the x-axis where I excite them to. And I have, this is the FID, the free induction decay here. So everything you've seen here is what we had in the FID experiment that we talked about already. And this decay now is a T2 star decay because when I first excite, right after the 90-degree pulse, everything is perfectly coherent and aligned with the x-axis. But if I give this a little time to evolve, I'm going to get phase dispersion like this. So this total signal is going to decrease faster than if everything was just perfectly on resonance. So this FID will actually decay relatively quickly. Then at this point in time, I do a 180-degree pulse along the x-axis. And if we were doing a live class, I would use my drumsticks or use my arms to give you an idea of what this looks like. But I think if you try, just follow what happens to these vectors here, you'll get a sense of what happens. So if I did a 180 across this axis here, what that's going to do is cause a rotation about that axis, 180 degrees, and it will flip it. So C, which is normally on this side here, now flips over here to the other side. And by the way, I'm assuming that I'm treating this as if that 180 degree pulse is effectively instantaneously fast. So we're ignoring processes during that pulse. We're just causing a very quick 180 degree, so we can make this a little simpler. So C flips over to that side, and likewise B flips over here. So you can imagine a rotation along that X direction. And so now right after the 180, you've sort of flipped the phase state of these different isochromats. But C is still going to rotate in this diagram here clockwise faster than B. So because of that, it's going to start coming faster in this direction relative to B. And if you wait the same amount of time, these two, they'll all come back together and be coherent again. So the time from the middle of this pulse to the middle of this pulse, if you take that time, which here is TE halves, is often called tau for spin echoes. So that duration, if you wait that duration after, then the exact phase dispersion will be refocused, and these will come back and be coherent again. And when they come back together, the total signal is increased, and that's what we call a spin echo. So in a spin echo experiment like this, you have your 90, 180, and as the echo is forming, you turn on your ADC and measure what's happening there. So I'm going to quickly go back and look at that web page from Lars Hansen, which I like so much, and he has a nice visualization of this. It's heating up my computer a bit. Okay, so this is, you can do this as well. You have the link to it. If I go to weak inhomogeneity here, that example, I've got a bunch of isochromats, but they're at equilibrium, so they're all lined up. I'm going to give them a 90-degree excitation. And they flip down to the transverse plane. And you can see them start to spread out. And that is the spread because they're all at slightly different B0 fields. Boy, this thing's really running slow. But that's T2 star decay. If you took the vector sum of these, you can see that the net length is smaller than the lengths of each of individual isochromat, the MXY of each individual isochromat. Let me reset this. I think it's running too slow to be useful here. There we go. Let's go back to the weak inhomogeneity case. I'm going to excite it again. It's still running slow. So it starts spreading out like this, and I wait a certain amount of time. Then I'm going to do 180 degree pulse. Let me hit that here. And what it's causing is a rotation. This time I rotated, like I showed you in the example, across the same axis they were aligned with in the first place. And now, as they become coherent again, they come back together. In this sample, they don't come back together perfectly. It's just kind of an artifact of the way he does it. But that's the idea of the spin echo. Things are spread out. The net vector is a little reduced, and you do a 180. And I could do it again, in fact. They'll keep coming back together over and over when I do these 180s, because I'm sort of flipping around the phase states of the different isochromats. I'm going to turn that whole thing off. And you can play with that a little on your own. So let's go back to this and say a couple more things about this. So I want to look at the spin echo experiment and compare the difference between T2 star and T2. So in this example, after this 90-degree pulse, this is the FID experiment. Now I have this free induction decay. And if there's T2, and the decay rate you see here is the T2 star decay rate. And that's because you have not just T2 processes, but also much reduced, much lost signal because of the inhomogeneity of your sample. And so, when the spin echo, so everything's dephasing, and at some point it's dephased so much so everything's pretty much uniformly distributed around the XY plane, and there's no coherence that's visible. So you're basically in the noise at this level here. I do my 180, and as these phases start to become coherent again, they start building up signal. So at this point, you might get a little envelope which is kind of like a minus T2 decay, T2 star decay. It's actually the T2 prime, and that's shown here. And then it forms this nice echo, and then again you have another decay here, and this is going to be a T2 star decay there as well. So the net, so each of these times you've got these smaller envelopes, which are faster decay, are your T2 star decays, and the total reduction of signal over time, it has to do with the T2 decay, and that's really you can think of that as the shrinking of each isochromat's the length of the vector, the MXY vector for each of the isochromats. That's what you see with the big T2 decay, and this is what you see from inhomogeneity between the different isochromats. And at the time where you hit a perfect spin echo, all that inhomogeneity is canceled out, and you sort of go back to the best case scenario, which is your T2 decay. A couple last things another way of looking at this is a tracking phase. And here I have another example. There's a lot of examples, but the spin echo is a very important topic. So here's another case here where, in this example, I have 3 isochromats, and I want to show you 2 different types of refocusing pulses. So here, right before my RF pulse, I've got these 3 samples, 1, 2, and 3, where 1 is faster and 3 is slower, but going in the other direction. So those are the off-resonance values. So at first, at equilibrium, they're all aligned. Immediately after excitation, they're all aligned here along the y-axis. And then if I wait this little time to let these phases accumulate, I've got some dephasing. So my 1 is over here, and my 3 is over here. In reality, this is going many, many times around, so it's much more complicated, but this helps us visualize it. So let's apply a 180-degree pulse, and let's start by applying one along the y-axis. So in this drawing, that's this axis here. So this horizontal axis. So let's follow this top path here. So if I apply a 180 along this axis, 1 is going to flip over to that side, like you see here, and 3 is going to flip over down there. But at the same time, 1 is going to continue going faster. So if I wait another tau, TE over 2 or tau periods, these things, 1 is going to catch up to 2, and 3 is going to slow down to 2, and you're going to get recurrent refocusing right here. If you go back to this point in time here, if I did a 180 around a different axis, the x-axis, that would be this axis here, as I've shown up, you can see it over here. If I do it across this axis, it looks like a very different thing. So I'm flipping everything over to that side of the circle, and that's what I'm showing here. Now 1 flipped from here to there, 3 flipped from there to here, but the net effect ends up being the same. So as 1 is still going faster, it's going to catch up to 2, and 3 is going slow relative to 2, so they'll come back again coherent at the same time. So these are 2 different types of refocusing pulses along different axes, and they both produce the same refocusing, but they produce it with different phase. The phase of this magnetization is different than the phase of that magnetization. And in fact, you can do a 180 across any axis, x, y, z, or some diagonal, and you'll still get refocusing. It's a little harder to visualize maybe, but the phase will depend on the angle that you applied that 180. It'll depend on the angle of the 90 and the 180 together. So another way of looking at these is what we call a phase diagram. This isn't an extended phase diagram, EPGs, you'll get to those later maybe. This is just a phase diagram. So what I'm plotting here is the actual phase accumulated by these 3 isochromats as a function of time. And so this plot here, let's start with this bottom plot here, which is the top path here with the 180Y. I guess I should have done that different. So if you look at how the phase of isochromat 1 accumulates, and when we do the 180 across the y-axis, which is here, this way, it flips. So 1 goes from positive, I don't know, that looks like 20 degrees to me, down to a negative 20 degrees. And then it keeps accumulating up there. And 3 goes the opposite way. As they all have an off resonance, which is linear. So the phase increases linearly with time, and that's the slope of those curves. And the times where all those coherences come back together and the net phase is 0 is when you have coherence and forming your echo. This is the same sort of plot, but with the 180 across the x-axis. So my 1 accumulates, I flip it over here, and that is right there. And it still accumulates at the same phase. That slope should be identical as the slope here. And you have the same phenomena that when these lines come together, you get a coherence. And that's what you see right at this point here. So these sort of phase graphs are just another way of plotting out these things and looking at how echoes form and when echoes form. These are very useful in very complex pulse sequences where you're trying to look at when you might get echoes forming unexpectedly. Is what's most commonly used for. Last couple things I want to say about spin echo. So we've been talking about this one up here, where you've got a 90, a delay of tau, 180, and an echo forming here. You can do that again. So at this point in time, everything's coherent, and so here's like my 90, 180. I can let that dephase again and throw another 180, and I'll get another echo coming out here. And that would be a double spin echo. You can also do it with different timing. So remember, the key thing is that those 2 time periods have to be equal to form that. The echo will form when this tau equals that value. So in this case, I do a 90 and a 180. and I'll get an echo to form here, and then I've got this long delay to that one, and then there'll be another echo forming when at this time is equal to that time. The time of dephasing is equal to the time of rephasing. Then you'll make a new echo here. And there's a certain experiment which is very famous and very useful called a car per cell Myboom-Gill or CPMG type approach. And the idea here is you have, with this type of pulse sequence, specifically you have consistent timing between your 90s and 180s, and you just do a whole series of these recordings. And the phase between the 90s and 180s has to be a specific relationship here, 90x and 180y. And that has certain characteristics that it replaces. It suppresses certain types of signal, which I won't go into great detail. Two other points I wanted to make is when we do these spin echo experiments, I'm saying it's got to be 180-degree pulse. But in fact, if you do something less than 180, and you really can never do a perfect 180 over a uniform part in space, you still get refocusing. These plots on these previous pages, if you do a 120-degree flip, it's a little harder to see how they refocus, but it does work. And in fact, most spin echo experiments, spin echo imaging on scanners do use pulses more like in the 120 to 140-degree range. You do get less signal. You don't get as much focusing, but it's a trade-off because it's kind of expensive to produce a flip angle that high. And secondly, if you were to measure T2 decay, for example, if I were to look at the expected signal over this echo time from 90 to here, and if I looked at it with this experiment, which we call Hahn spin echo, named after Erwin Hahn, or this one with the car per cell spin echo, I would see that the decay, the effective decay I measured here, is actually less than the decay I would measure here. This has to do with the complexity of what contributes to T2 decays. Some of the components that contribute to T2 depend on how quickly you refocus them. So things like diffusion, which actually reduces T2, is effectively refocused with a tight set of 180s like this, so they're constantly being refocused. Whereas diffusion doesn't, those effects don't get refocused in this case. So if you did a Hahn spin echo and tried to measure a T2 value, you'd find a shorter T2 value with a Hahn spin echo than with a car per cell. And that's about all I want to go into with that. So for now, that concludes this particular lecture. This was the continuation of 1.3, and the next one will be on image encoding.